webinar cycle of the SCOR Foundation for Science. Today, I have the pleasure and the honor to introduce Christian Gaulier, who is with us. And despite having had some anxiety concerning a delayed flight in the US and in Canada, Christian is professor of economics at the Toulouse School of Economics, with which the foundation has a share and support a share. And Christian is the executive director also of Toulouse School of Economics and working very tightly with Jean Tirole. He has been a past president of the European Association of Environmental and Resources Economists, a winner of the Paul Samuelson Award, and a lead author of the 4th and 5th reports of the Intergovernmental Panel on Climate Change, IPCC. Let me remind you that the IPCC shared the Nobel Peace Prize in the year of the report's publication for his work. Extending its previous work at the IPCC, Christian Gaulier will today challenge the common wisdom that a relevant taxonomy, by differentiating brown industry from green ones, would promote the needed transition out of the non-renewable energies. But economic behaviors are dynamic by nature and will adapt to the right incentive to green the economy. Therefore, pricing or taxing carbon emissions to internalize the external costs of carbon emissions for the planet will give such an incentive to all industries and help design a welfare improving transition path. Of course, the price or tax level depends on how much we care, we all, you, myself, Christian, and the world population is caring about the future of the planet, which is an equivalent, but maybe Christian will explain that, of our discount rate. Thank you, Christian, to have accepted to introduce us to this dynamic view on the energy transition, which is very important for all the industry, because of their commitment first, and because it's a more general risk and macroeconomic concern. Let me add that you can find the complete work of Christian on the topic either on the website of the Toulouse School of Economics or for a selected subsample by clicking on the Share Risk, Markets and Value Creation with the Toulouse School of Economics inside the website of the SCOR Foundation for Science. Of course, Christian has also written many books you can find very easily on Amazon. Please, Christian, you have the floor for how long you wish on this fascinating topic, probably 1 hour. We will thereafter open the discussion for questions by the auditors and answers by you. You have the floor, Christian, and thank you so much.
Thank you, Philippe. Thank you for the invitation, and I'm sorry for being a little bit late, but the last 12 hours has been quite difficult. Do you see my screen?
Yes.
Okay, good. So, two things as an introduction. First, on the issue of carbon pricing. Carbon pricing is, in fact, a way to estimate the benefits of reducing emissions of CO2. So, when you do, for example, decarbonization of the steel industry or decarbonization of transportation, you have a cost, sometimes large cost, and you have benefits. And the benefits correspond to the damage that will not materialize because you don't emit the CO2. Okay, so because those damages that are risky because you don't emit CO2 today, these damages is in fact a flow of damages that will materialize over decades and even centuries. So the issue of carbon pricing, the value carbon, is really an asset pricing issue. How do you value a flow of damages that will not materialize because you don't emit the CO2? So I will heavily rely on the asset pricing literature to explore different issues related to risk and uncertainty surrounding the climate change problem. So that's the first point. The second point I want to express before going into the details is, when we think about carbon valuation, we often think about carbon tax or, a market for permits of CO2 emission. That goes one step too far with respect to the initial project of a carbon valuation. Carbon valuation is really about comparing costs and benefits. We relatively know well the cost of abating an energy transition. We need to also, in front of this cost, we also need to put a value on the benefits. Okay, and so in order to determine what action, I mentioned, for example, decarbonization of the steel industry, which is probably rather expensive. Decarbonization, for example, of the airline industry, which is even more expensive. Decarbonization of, heating system in houses, decarbonization of transportation. All those things have different costs, some small, some large. Where do we stop? Where do we decide that the cost becomes too large? The private costs or the current costs are too large compared to the environmental and ecological benefits. So those questions correspond to the issue of carbon value. So what's the carbon value? Is it if it's, for example, $190 per ton of CO2, this means that we should do all efforts that cost us less than $190 per ton of CO2. If we believe that $480 per ton of CO2, we should do much more. We should also do all efforts that cost us between $190 and $480 per ton of CO2. So these issues of cost-benefit analysis to determine among the myriad of possible actions to reduce emission, what are the socially desirable action and what are the socially undesirable green action. The difference between the two is whether the current cost of the effort is smaller or larger than the carbon value. So that's what I wanted to say. This is related to taxonomy, as mentioned by Philippe. The taxonomy is an approach, has been an approach, in particular EU taxonomy has been an approach to determine precisely what is green and what is not green. Okay, what is socially desirable as an energy transition effort and what is not socially desirable as an energy transition. I'm not sure, I must tell you, but I will not go into the detail. I'm not sure what is exactly what has been done for the EU taxonomy has been done in line with this big picture of comparing cost and benefits of the myriad of potential action to reduce emission. Okay, we could talk about nuclear, we could talk about natural gas, things like that, but I will not do that today. I'm sorry. Maybe you will come back in the question. So here on this slide, as an introduction, you see the most recent attempt to estimate the value of carbon. Okay, this attempt has been made by the US Environmental Protection Agency, EPA, and it has been published last November. Okay, in fact, last September. I discovered it in last November, in fact. And so you see that this document generates this table, and this table gives you the social cost of carbon, the carbon value, the present value of the flow of marginal damages generated by 1 ton of CO2 emitted today for different possible discount rate. Capital R could be 2.5%, 2%, 1.5%, and give you for each of these discount rate the schedule of carbon price for the next 3 decades, 2020 to 2090. I'm sorry for the typo, 240. So you see, of course, the larger the discount rate, the smaller the social cost of carbon, because when you use a larger discount rate, you get a smaller present value of the flow of net benefit or marginal damages. Okay, so you see that a small difference in the because of the very long maturity of the damages generated by CO2, you see that the discount rate is critically important to determine the social cost of carbon. And I would like to focus most of my presentation on this issue of what discount rate should be used in order to determine the social cost of carbon. And you see this is a critical question because in this table you see that a small change in the discount rate has a large impact on the social cost of carbon. So this choice of the discount rate is related to a deeper issue, which is whether or not in our society, in our economic system, do we take care enough about future generation and sustainability issue? The answer to those questions, the operational answer, I should say, to those questions is really dependent on the choice of the long-term discount rate. If I use a small discount rate, I will not penalize too much future benefits because they happen in the long distance, compared to a situation where I take a larger discount rate, in which case I will penalize much all actions that have long-term benefits. Okay, for example, in the US, the current discount rate to evaluate that kind of sustainability issues, the social cost of carbon, the official discount rate is still 7%, which is quite crazy, in fact. So when we think about discounting, that is, when we think about penalizing the future because it's the future and not the present, why do we discount the future? Why do we penalize the future because it's the future? Well, we do that for two main reasons. You probably, as actuaries, you know the second reason. Let me first take the first reason, which is more normative. The first reason we discount the future, that's because we believe in economic growth. If we believe in economic growth, future generation will be wealthier than us. And so the question, why should we invest for the future? Because investing for the future means asking the current generation, the poor, to sacrifice something for the benefits of future generation who will be wealthier. So that will increase intergenerational inequalities. And if we are inequality averse, I think we are, we should penalize investment because they increase intergenerational inequality. So that's one basic important reason why in economics we discount the future. You know better probably the other reason why we discount, which is the shadow cost of capital, the opportunity cost of capital. Okay, if we invest in energy transition, the capital we invest there could not be invested somewhere else, and this somewhere else may provide some positive return, and therefore you need to make arbitrage between the energy transition and other investment in the economy that brings other returns for future generation. We should invest in this energy transition only if the social rate of return of this energy transition is larger than the return in the remaining of capital in the remaining of the economy, and so that provides another reason why we should discount the future. I will mostly focus on the first argument, which is normative. Okay, because I think that when we think about whether we should sacrifice for the present for the future or for climate change, it's mostly a normative question. So that's these two reasons. The shadow cost of capital and economic growth are two reasons that materialize without uncertainty. Even under certainty, we should discount the future. There is another reason we discount the future. Well, that's because most of the action we perform today have uncertain future benefits. Okay, and if those future benefits are uncertain and increase the macroeconomic risk borne by future generation, because future generation are risk averse, well, we should penalize those investments because they increase the macroeconomic risk. On the contrary, if we do action today that tends to reduce the macroeconomic risk for future generation, those actions will generate an insurance value. Okay, if the net benefits of investing in abatement of emission generate more benefits in the worst state of nature for future generation, you see this negative correlation mean in a sense that the energy transition not only reduce damage in the future, but they also generate more benefit in the worst state of nature, and that's played the role of an insurance contract. So, and then the issue, of course, and I will you take 5 minutes talking about that at the end of my presentation. And the question is it true that the energy transition not only reduce climate damage in the future and expectation, but they also reduce more damages in the worst state of nature. Therefore, does climate change, does fighting climate change reduce the risk borne by future generation? That would justify using a smaller discount rate and therefore using a larger social cost of carbon. So my talk will be split in 2 pieces. The first piece will be just reminding you this basic argument for why we discount the future in economics under certainty, and that will introduce the notion of the Ramsey rule. And then in the second part, I will look at what's the effect of uncertainties on this discount rate and therefore on the social cost of carbon. So historically, economists have been developing integrated models that integrate climate module with economic modules, let them interact with each other, the climate interact with the economy, and that generates some dynamics, climate dynamics and economic dynamic, prosperity and economic growth that generate emission generate climate damages, and that affect growth. Okay, that kind of integrated assessment models. So historically, those models, the DICE model, for example, of Bill Nordhaus, have been assuming no uncertainty. Okay, in those models, we know the economic growth, we know the growth of total factor productivity, we know the climate sensitivity parameter, we know the relationship between increased temperature and aggregate damages. We know everything in those models, and then there, in that kind of model, we just get the basic reason why we discount, which is this argument for the fact that assuming economic growth, fighting climate change, generate benefit for future generation who will be wealthier than us, and therefore we should penalize that by discounting those marginal damages. So in those models, in those integrated assessment models, where they do not really talk about a discount rate, what they do, they just look at in a public economics approach, which consists in defining a collective objective. When I say collective, I mean intergenerational objective. Let me assume that we measure the total welfare of the flow of generation of people who will live on this planet through taking the discounted expected utility of their flow of consumption. Okay, so each generation will benefit from some prosperity, from some consumption level. They will extract utility from this consumption, and therefore, for each generation, I can measure a level of welfare, and I can aggregate this wealth in generation and welfare by discounting this flow of generation and welfare that will generate intergenerational social welfare. Okay, if you do that, and if you assume that there is an increasing and concave relationship between consumption and utility, okay, generation who consume more will get more utility, but this relationship is concave. That is, a very wealthy generation will have a smaller increase in utility for a given increase in consumption. Okay, and that's concavity of the utility function embed into the model this notion of inequality aversion. So suppose that we are in a growing economy. Suppose that total factor productivity will continue to grow in the future as it did over the last 2 centuries. In that case, in spite of climate change, it is expected that future generation will be wealthier than us, okay, and therefore investing for the future will raise intergenerational inequalities. Okay, and therefore we should penalize those investments by discounting at the positive rate. Okay, so that kind of this methodology is embedded into the model. Let me give you more details about that. So in those integrated assessment model, as I said earlier, we measure for a given climate policy, we measure the flow of utilities enjoyed by each generation. So if the flow of GDP per capita is defined as CT, C0, C1, C2, C3, and so on, where CT is the consumption level enjoyed by generation T, and if I make a link between the level of consumption and the level of welfare or utility of that generation, I have this function capital U of C, okay, that measures this welfare. Okay, so each generation will enjoy a level of welfare U of CT, and in order to determine what's my intergeneration objective of the social planner to determine what's the optimal climate policy, what I will do is I will add up this flow of utilities enjoyed by each generation. I will take the integrals, as you see in the central equation of this slide. I will take the integrals of the flow of utility discounted as some rate delta, which is a rate of pure preference for the present. It's a form of egoism of the current generation compared to the future generation. I will weight the flow of utility of the future at a smaller rate than my own utility at 0, U of C0. And because CT is potentially uncertain, I take the expectation of this discounted utility. So I get a discounted expected utility model, which is standard everywhere. In economics, there had been transformation of that basic models, but we could talk about that during the discussion. But I still believe that this discounted expected utility model is the best representation of our moral preference or normative preferences when we think about what to do for the future. Okay, where I could talk about the veil of ignorance, I could talk about the independence axiom, but I will not do that today because of lack of time. I also assume, as standard in finance, asset pricing and macro literature, I will take a constant relative risk aversion. So the utility function is a power function of future consumption. And gamma that you see in this equation, gamma is the degree of concavity of the utility function. That is the degree of inequality aversion in the model. It's also a degree of risk aversion, in fact, this concavity of the utility function. But you know that under the veil of ignorance, talking about risk aversion or talking about inequality aversion is the same thing. Okay, so now let's talk about valuation. So let us see how a specific benefits occur materializing at some future date T affect welfare. And rather than measuring the welfare benefits of a sure benefit B materializing in T years in utility term, I would prefer to measure it as a standard in monetary term. So I will define the present value, the value today of a sure benefit or sure P of B occurring in T years, that's PV, present value. Okay, and this PV, if I pay PV today, if I accept to sacrifice PV today, and to get B in T years from now, my level of utility will be the same as in the status quo. So that's, you see that PV is then the maximum, the willingness to pay today to get this sure benefit B in T years from now. There is a question here? No. Okay, so be sure that switch off your microphone. Okay, so this equation on top of this slide provide the definition of the present value. It's the willingness to pay today to get this benefit BT in T years from now. Okay, So making the assumption of marginal changes, B small, PV small, and therefore you do you do linear approximation of the utility around C0 and CT, and you get this PV expressed in as a second equality in this slide. PV is some term time B. So this term is a discount factor, obviously, and this discount factor, from that discount factor, you can define a discount rate, RFT, okay, and when you identify RFT, you get the third equation on this slide, which is RFT, the discount rate, to value a sure benefits materializing in T years from now. It is given as delta, the rate of pure preference for the present, minus a term, which is, as you see here, the inverse of T times the log, the natural log of the expectation of CT of C divided by C0 power minus gamma. So in the next few minutes, I'm going to calibrate this simple asset pricing equation that you see in most consumption-based asset pricing models, like the consumption-based consumption-based CAPM. Okay, so the simplest way to do that is to do it as in these historical integrated models in climate, in climate finance and climate economics. Let me assume that CT grows at a constant rate G. Okay, so CT is equal to C0 times the exponential of G times T. So G is the growth rate of consumption. Okay, and then if you plug this assumption into this equation for RFT, you get the last equation on this slide. You get that RFT is just equal to delta plus gamma times G. Okay, and we call that the Ramsey rule. Okay, this formula is famous. It has been discovered by in 1928 by Frank Ramsey, a Cambridge economics professor who died very young and produced two famous papers, one generating the Ramsey-Boiteux rule and one generating this Ramsey rule. And so you see that this Ramsey rule translates in mathematically, in mathematical terms, the idea that I provided earlier, which is in a growing economy, G positive, okay? Investing for the future increase intergenerational inequality, and therefore, in order to accept to invest in a risk-free project, you need that the internal rate of return of that project is large enough to compensate for the fact that this investment project increased the intergenerational inequality. And so that's why you see in this equation, this second term of the right in the right-hand side, which tell you that if gamma is positive, if you are inequality averse because your utility function is concave, which is the case when gamma is positive, when gamma is positive, the fact that you are in a growing economy, G positive implies that you should have a positive risk-free rate. So that's you see the translation of this normative idea that inequality aversion should matter to determine how much to penalize the future, because the future is the future and future generations are wealthier than us, translate into an equation. Okay, so how can we calibrate this Ramsey equation? Okay, well, that's bring me to the clash of 2007 between North American people represented by William Nordhaus and people more in Europe represented by Nicholas Stern. Nicholas Stern in 2000, at the end of 2006, publishes Stern report. And this Stern report provided calibration of an implicit calibration of the Ramsey rule, which is quite different from the implicit calibration of the Ramsey rule used in Nordhaus' DICE model. So Nordhaus typically in the DICE model make the assumption that delta, the rate of pure preference for the present, the way I penalize the future generation in my social welfare function at 1.5%, which is very large. Okay, gamma, the degree of concavity of the DT function, is assumed by Nordhaus to be 1.45, and G, the growth rate of consumption, remember there is no uncertainty in DICE, is assumed to be forever 2.15%. And so therefore, when you apply this, when you calibrate the Ramsey rule using these numbers, you get a discount rate of almost 5%. Okay, and when you use a discount rate around 5% to calibrate a social cost of carbon, a carbon value, discounting the flow of marginal damages, you get not much. You get something like $20 per ton of CO2, and that's why Nordos for a long time was a climate economist that supported the idea that we should not do too much to reduce emission. We should only sacrifice. We should only do efforts that has a cost per ton of CO2 saved smaller than $20. Okay, so that there are not many actions like that, in fact. Stern came in 2007, calibrate the Ramsey rule, saying its delta is not 1.5, it's 0.1. Gamma is not 1.45, it's 1, and the growth rate is not 2.15, it's 1.3. Okay, and when you use those alternative numbers, you get a much smaller discount rate of 1.4%, and that, of course, with its much smaller discount rate, you generate a much larger social cost of carbon, around something like $200 per ton of CO2. Okay, so okay, so let me give you an overview of course, there is an issue about what are those parameters gamma delta. Well, gamma, I will say a few words about that later. Let me focus for the time being on gamma. Okay, gamma is the degree of concavity of the utility function. Different authors have provided different estimation of this gamma, which measure the degree of inequality aversion. You see, when you look at those numbers, you get consensus around 2. Okay, and gamma equal to represent a relatively good consensus, but with of course some deviation around this mean. Gamma equal to seems to be supported by majority of economists. Okay, so let me also say a word about delta. Well, delta, you know, you implicitly I implicitly mentioned that. I mean, delta different from 0 is normatively unacceptable. Okay, using, I mean, penalizing future generation because they are born after me, which what I would do by using a positive delta make no ethical sense. Okay, so I typically use delta equals 0 in my calibration in my papers over the last 20 years. As I said earlier, I assume gamma equal 2. And then the last parameter to calibrate in the Ramsey rule is G. Okay, and you see a big difference between Nordos and Stern is that Nordos assume a much larger growth rate of the economy than Stern, and that's mostly explain the difference between the two discount rate and therefore the big difference between the two social cost of carbon. Well, okay, I will not say Stern or Nordos is right. I mean, the reality is we don't know what will be G, and in fact, G is uncertain. And we need to recognize that uncertainty, that central uncertainty about the destiny, the economic destiny of future generation on this planet. Okay, and so we need to plug into the model the true nature of economic growth, and this true nature is uncertain. And therefore, there is this issue of what's the consequence of this uncertainty on the carbon value. And that's what I want to discuss with you in this second part of my presentation. So there are two reasons, there are two impacts, I should say. There are two impacts of uncertainties on the social cost of carbon and on the discount rate. The first impact is prudence. Okay, if the future is uncertain, it makes sense to do more effort today, to accept more sacrifice in the presence of this future uncertainty. And this very simple idea or intuition has been developed, for example, by John Maynard Keynes in his idea of having precautionary saving. Okay, people save because they face uncertainty and they want to accumulate some precautionary savings in order to be able to smooth their consumption over time. When there be shocks, positive or negative shocks on their incomes. Okay, so people accept to do more short-term sacrifices in their consumption, that's saving, when they face more uncertainty about the future. Okay, and so what is desirable at the individual level is of course socially desirable at the collective level. So how do we collectively do more effort because we face uncertainty about the future? Well, we reduce the discount rate. By reducing the discount rate, more investment projects will pass the test of a positive net present value. Okay, so in fact, when you go back to the original pricing formula that you see at the middle of this slide, okay, you see that you can now, if I replace this assumption that CT grows with no uncertainty at rate G by assuming that CT grows stochastically following a geometric Brownian motion, I can estimate this expectation of CT divided by C0 at the power minus gamma under this assumption of a geometric Brownian motion. Okay, because I know that this implies that log of CT will be normally distributed, and the Stein lemma will allow me to solve for this integral. And if you do that, okay, if you make this assumption that you can represent the uncertainty surrounding the future by a geometric Brownian motion for the growth rate for consumption per capita, you get a new representation of the risk-free rate. Okay, this risk-free rate RFT, I assume delta equals 0. Okay, this risk-free rate is now equal to gamma mu. Mu is the trend of growth of the geometric Brownian motion. So this first term is just the Ramsey rule, but you need to modify the Ramsey rule by subtracting from this Ramsey term a correction that is proportional to the variance of the growth rate of consumption. Then sigma is the volatility of the growth rate. Okay. The problem is that this extended Ramsey rule, provide a reduction. First, you see that indeed taking into account of risk induces to reduce the discount rate. Okay, so that has necessarily a positive effect on the social cost of carbon. Okay, and this is just an idea of prudence. But when you plug numbers, when you calibrate this extended Ramsey rule, you do not get much. Okay, the volatility of the growth rate of consumption over the last century has been something between 2 and 3% in most Western countries. So when you take gamma equal 2 and you take sigma equal 3%, you get almost nothing. You get 0.2%. So you take into account of the riskiness surrounding humanity for the remaining of the days of the lifetime of this planet, only reduce the discount rate by 2%, the risk-free discount rate by only 0.2%. So that is very small, and it's very frustrating that, you know, crucial risk for future generation may mean not much about, you know, the choice of the discount rate, and therefore the choice of the social cost of carbon, and therefore on the determination of the intensity of the effort to reduce emissions today. So that's a problem. I will come back on that, what we call the risk-free rate puzzle in a minute. Before going back to this issue, let me introduce to the second reason why we need to take into account of risk when we determine the discount rate. The second reason is not about the global risk, okay, and the risk-free rate, but it's also the necessity to adjust the discount rate to the risk profile of the project you contemplate. Okay? And so this idea of adjusting the discount rate to the risk of the project, okay, that you also find in the asset pricing literature. I invented nothing there. So in the previous slide, you remember I assume B, the future benefit is certain. So let me assume now that B is uncertain, and it's related to the macroeconomic uncertainty surrounding CT. Let me assume that the benefit BT is equal to CT at the power beta. For some parameter beta, this parameter beta is the income elasticity of the net benefits of your project. So if beta is positive, the investing in that project increase the macroeconomic risk because the benefits is positively linked to aggregate consumption. If beta is negative, that's the opposite. You have with a negative beta, you get an insurance project because it provides more benefits in the worst state of nature when CT is small. So it's exactly as providing indemnity in poor state of nature. Okay, so beta is a parameter that characterizes, the correlation between the benefits and the aggregate consumption, and the sign of beta separates a project that increase the macroeconomic risk when beta is positive, and project that reduce the macroeconomic risk, that edge the macroeconomic risk, or that ensure the macroeconomic risk that's related to project with a negative beta. And so you can again go back to the original asset pricing formula, which is here, but you need to extend it to B being uncertain, B being equal to CT at the power minus gamma, at the power beta, sorry. I didn't represent this equation in my slide because of lack of time, but you basically do a similar exercise. You also use the Stein lemma in order to estimate the expectation of a power of CT. And you get this simple asset pricing formula where the risk-adjusted discount rate you need to use to evaluate a project whose income elasticity of net benefits is beta. You need to adjust the risk-free rate by adding beta times a constant gamma sigma squared, which is which I refer to as the aggregate risk premium. Okay, so you see that you need to adjust positively the discount rate when beta is positive, because gamma sigma squared is of course positive, and you want, on the contrary, when beta is negative for projects that ensure the macroeconomic risk, at least partially, you should use a discount rate which is smaller than the risk-free rate, and you see the translation of this insurance value into using a smaller discount rate for those projects, and that will increase their present value. Okay, so the problem is, we have the equity premium puzzle typically in this kind of model. When you calibrate the parameter gamma sigma squared that multiply beta to tell you that by how much you penalize or provide bonuses to projects that increase the macroeconomic risk or that edge the macroeconomic risk, this gamma sigma square is again very small. Okay, again you get something like 0.2%. So that's so you in theory here you need to adjust the discount rate to the risk profile of the project, but not much. Okay, and that's quite contrary to what we observe on the market. On the market, we see that assets that are very risky require a very large risk premium in order for investor to accept to invest in those projects. Okay, so that's, and so you cannot easily reconcile this observation of market prices to this formula. So that's why in the models, in my models, I standardly use now I abandon the assumption of a geometric Brownian motion to recognize that long-term risk, and the risk surrounding the distant future of this planet cannot be just represented by a geometric Brownian motion. Okay, and in fact, I'm making the assumption of a geometric Brownian motion tends to vastly underestimate the risk for the future. And if you underestimate the risk for the future, of course, the consequence of that is you underestimate the risk premium and you overestimate the risk-free rate. Okay, just let me give you one example, one or two examples. One example is, if you really think that the growth of the prosperity of humankind of this planet can be represented for the next millennium by a geometric Brownian motion, I would like you to tell me what trend of growth mu you would put into the model. Okay, that's. I hope that you will realize that it is not just impossible to determine what's the mu for the next millennium. Okay, some economists like Larry Summers, for example, say, yeah, you know, we are in a secular stagnation, maybe a millennium stagnation, because we already discovered. I mean, science will make no more progress. Technology will make mostly no more project, and therefore those engines of growth, economic growth, will disappear, has already partly disappeared over the last 2 or 3 decades, and that's the end of the story. Okay, so maybe the mu is very small. Other people will say the opposite. Okay, that we will continue to make strong discoveries, that we will conquest the space. And so on and so on. So that's one example of a problem related to calibrating the Ramsey rule or the extended Ramsey rule or the aggregate risk premium made on the assumption of geometric Brownian motion. We also know that, you know, when you look at the past data of economic growth, you have a lot of extreme events, much more. The frequency of those extreme events is much larger than what you get by just estimating the density function of a normal distribution with the mu and sigma. So you have pandemics, we have war, we have financial crisis, we have Greece, we have, you know, Argentina. All those things illustrate the fact that there exist extreme events. Those extreme events are uncertain probabilities, and recognizing these parametric uncertainties on those probabilities should count when we think about measuring our beliefs about risk for the future. So let me just illustrate that with a simple example. Here I propose the simplest extension, I think, simplest extension of the geometric Brownian motion by recognizing that the trend of growth, mu, is uncertain. Okay, and let me very simply, just as an illustration, okay, in my papers I go to much more general and rich version of that. Let me here just assume that the trend of growth, we know it's a constant, but we don't know which constant is it. It could be 1%, it could be 3%. Okay, we will learn that in the future by observing growth, but at this stage we don't know. Okay. And let me represent this I don't know by putting the same probabilities to the 2 possible trends, 1% and 3%. And let me, on these 4 graphs, let me represent the density function of log of CT, which will be normally distributed because of geometric Brownian motion, in this case where in the benchmark where I assume that growth take value 2% with probability 1. Okay, so this, so I represent this benchmark where there is no uncertainty on growth, where the growth is mu equal taking value 2% with certainty, by the dashed curve on those different graphs, and I compare this density function of the benchmark to the density function when I recognize that mu is uncertain. For short maturities, you get this graph on the upper left part of this slide. You see that for a 1-year horizon, the 2 curves are almost the same, meaning that the uncertainty surrounding the trend does not matter to define the degree of uncertainty for next year log consumption. Okay, most of the uncertainty comes from the volatility of the growth rate. But if you go to the other extreme on the graph on the lower right of the slide, where it corresponds to a maturity of 200 years, you see that for the next 200 years, of course, the uncertainty surrounding the trend has a huge consequence on the uncertainty surrounding the what level of consumption will be enjoyed by the future generation living at that time. And you see, in fact, this trend, this uncertainty on the trend of growth put heavy tails, I mean, not heavy tails to the distribution of log of CT. And so that illustrates that for short maturities, introducing uncertainty on the trend will have almost no effect on asset prices, because the risks are almost the same, but for very long maturities, this uncertainty on the trend will magnify the risk compared to the assumption of the geometric Brownian motion that I made in the previous slide. And therefore, when you recalibrate this fundamental asset pricing formula that I presented earlier, you get that kind of term structure of interest rate, of discount rate, I should say, sorry about that. For each possible beta, beta, remember, it's the risk profile of the project. Beta equals 0 correspond to a risk-free project. Beta equal 1 correspond to a project that has a risk profile similar to the evolution of GDP. So in fact, it's a claim on GDP, if you prefer. Beta larger than that, beta negative. So you see there that you have a term structure compared to the geometric Brownian motion, where the discount rate are independence of the maturity. Here, recognizing that the parametric uncertainty will generate term structure which are not flat. For example, as I said earlier, the discount rate for risk-free project will have a decreasing term structure. Well, why? Remember, precautionary saving motive. If the future is more uncertain, you need to use a smaller discount rate. Okay, and because risks increase faster under this in this model than under geometric Brownian motion, that will have an effect to generate a smaller discount rate for risk-free project with the long maturities. On the contrary, for very risky project like beta equal 2, so project that really increase a lot the macroeconomic risk because they are their net benefits are very sensitive, positively correlated with aggregate consumption. You see that because of the large surrounding future consumption, the uncertainty surrounding the net benefits will be even larger, and the risk premium will be very large. Okay, so now so that's it for what I wanted to say about discounting system. Okay, what matters when we think about uncertainty and the way we should penalize the future, because the future is the future. Okay, so that's what I wanted to say on the discount rate. So let me apply those discounting systems to the case of estimation of the social cost of carbon. So I need to take into account of the different source of risk in this when I think about the social cost of carbon. So the social cost of carbon is when the future climate damages are uncertain for different reasons. Or more generally, I need to introduce in my integrated model, compared to what DICE has done with no uncertainty, I should introduce uncertainty on economic growth, and that will affect the discount rate, as I explained over the last 30 minutes. I should also recognize the deep uncertainty surrounding climate change. We all know for certain now that increasing concentration of the CO2 in the atmosphere will increase average temperature on this planet, but there is still a lot of uncertainty on the intensity of this phenomenon. And here I take a picture of different density function for the climate sensitivity parameter. You remember, maybe you don't know, but the climate sensitivity parameter is used by climatologists and economists to measure by how much the average temperature will increase when you double the concentration of CO2 compared to the historical level that prevailed before the 19th century. Okay, and so this parameter is uncertain, quite a lot of uncertainty surrounding that, and so different authors have been estimating the density function for this parameter. And so you see that first, most authors recognize density functions that are widely dispersed, but also different authors differ in their estimation of this uncertainty, and so that's an important issue. The second issue related to damages is not only we don't know by how much the average temperature will be increased, but we also don't know how much damages will be generated for a given increase in temperature. So on this slide, I represented different estimation of the what we call the damage function. By how much GDP will be in percentage will be reduced by a given increase of temperature, 2 degrees, 3 degrees, 4, 5, 6 degrees Celsius. So you see, of course, larger temperature increase will generate more damages, but probably in a convex way. But you see that different authors, one author, one curve, different authors disagree a lot about the intensity of the phenomenon. So there also there is a big uncertainty. So if I go back here, you know, I would like to know what beta I should use for climate to estimate the climate discount rate. At which rate I should discount the flow of marginal damages to estimate this carbon value. Okay, and you see, depending upon whether the climate beta is 0 or 1 or 2 or -1, I will get very different discount rates to estimate the social cost of carbon, and therefore I will have very different social cost of carbon. So the problem is we don't know much about that, and I'm sorry, you will be disappointed because, you know, there will be a lot of guess making in this in the conclusion of my presentation here, but that's just a lack of scientific information on this issue. So in fact, I don't know what is this climate beta. Okay, I have some beliefs, but truly there is absolutely no consensus in the profession about this beta. So and let me explain why this is highly controversial. But why? That's because we have typically two opposite stories related to the climate beta. We have a negative beta story, okay, which and we have a positive beta story. The positive beta story is simple, okay. Most models assume that climate damages are proportional to wealth. Okay, you insurers, you know that, you know, if you have a climate catastrophe, those catastrophes will be basically twice larger if wealth in the surrounding area is twice as large. Okay, so climate damages are proportional to wealth and consumption. And if climate damage are proportional to consumption or incomes, the beta, the income elasticity of climate damages will be close to 1. Okay, so that's a positive beta stories. We should not care too much about climate change because most of the damages will materialize in good state of nature when we will be wealthy. Okay, so that should induce us to use a large discount rate, and if we use a large discount rate, the social cost of carbon will be small, and we should not do too much. We should not do too much to reduce emission today. Because you know, if climate damages are important, just because future generations will be so much wealthier than us. Okay, so but there is a negative beta stories, and many economists in the public opinion and think that this negative beta stories is prevalent. So the idea is suppose that the main source of uncertainty. We don't know whether doubling the concentration of temperature of CO2 in the atmosphere will either increase temperature by 1 degree or by 4 degrees. Okay, and let us consider an extreme information that tell you, in fact, climate sensitivity is much larger than expected. It's 4 degrees, not 1 degree. Okay, in that case, you will have large damages. Okay, if you have large damages, you have low consumption because the future generation will have to face those damages at the same time, where having reduced emissions of CO2 in the past would have had a large benefit today. So you see that you have a negative correlation between the net benefits of climate abating emission today and aggregate consumption in the future. And therefore, the beta is negative. The income elasticity of the marginal damages, therefore, of the net benefits of reducing emission today, this beta is negative Okay, meaning that most of the benefits of fighting climate change will materialize in the worst state of nature for the future generations, and that provide an instance benefit for those future generations, and therefore we should recognize that in the way we value carbon. And the way we should do that is to accept to use a smaller discount rate, even a discount rate smaller than the risk-free rate, and that will generate a high social cost of carbon, which will induce us to do much more effort to reduce emissions today. So just to illustrate this problem of we don't know what's the beta, let me just give you two illustrations of that. One has been made by myself and co-author Louise Kessler and Simon Dietz in 2017, where we estimated, we just used the DICE model. Remember the Nordos DICE model has no uncertainty. So what we did is quite simple. We Monte Carlo simulated the DICE model for the next 600 years by taking randomly the different parameters of the model. So we allow for uncertainty on the total factor productivity, so the intrinsic growth of the economy. We allow for uncertainty on climate sensitivity. We allow for uncertainty about the degree of concavity of the damage function, and so on and so on. And when you Monte Carlo simulate that, you get that kind of clouds of estimation for the future consumption C1 and for the future marginal damage S1. Okay, and you see that typically you have a positive link between future consumption and future marginal damage, and therefore the beta is positive. And in this model, you can estimate the beta for a time horizon of 50 years at around 0.7. So that's a situation where, you know, this climate negative beta stories is not strong enough to reduce the beta a lot below 1. But I have another, so I did that during over the last few months. I look at an alternative models to DICE. This is a model that has been published in Econometrica around 10 years ago by Golosov and co-author. I will not go into the details, but then it's quite different. In particular, it assumes that climate change affect the rate of growth of consumption rather than the level of consumption. I will not go into the detail there, but just look here that I get here a different cloud, okay, linking future consumption and future damages. So here you see a negative relationship between the two. The beta is negative, and the beta is quite largely negative, minus 3.5. So where does it bring me this? Because I have 3 minutes to go here. Where do I go with this? Okay, so I know that beta is smaller than 1. Okay, the positive beta stories bring me a beta equal 1, but there is an opposite story that tell me the beta is if I recognize that climate sensitivity is uncertain, that will reduce the beta. By how much, I don't know. Okay, different models give me very different answers. The DICE model give me I should reduce beta from 1 to 0.7, and the Golosov model tell me, oh no, beta is become even largely negative. Well, I tend to like more, I mean, to believe more in the DICE model than in the Golosov model. The Golosov model is still under scrutiny in the profession. Not many people use that alternative model. So let me say, and here you see, that's where I make my guess, okay? And that's, don't know whether it's a clever guess or no, but probably, I mean, the climate beta, given the scientific knowledge we have about that, is probably something somewhere between 0.7 and 0. So meaning that if you look at time horizon correspond to the maturity, the duration of the flow of marginal damage, which is between 80 years and 120 years, you see that you should use a discount rate, you know, between 1% and 2%. Again, you see, this is not very scientific, but that's really what I can, the best thing I can tell from what I've been presenting and what I've been working on over the last 20 years. And then you see there how much remain to be done in order to get finance answer to the question of what is the discount rate to be used and what's the social cost of carbon. So so here is my conclusion. I have a third section where I talk about an alternative approach to the social cost of carbon, where I recognize that we have, rather than comparing costs and benefits, I look at a solution where politicians have determined to make sure that we will not cross the 2 degrees Celsius threshold. And therefore, in that case, we have a intertemporal carbon budget. And from that intertemporal carbon budget, the question is how to allocate the intertemporal budget over time. Should I do it now? Should I do more effort now? And that will allow me to make less effort in the future. So there is an issue which is, I think, not well performed by the current analysis made by climate economists, but I have no time to spend on this alternative approach to the social cost of carbon. I will give you my slide if you want to look at that. I have a paper associated to that, but for this approach consisting in putting a value to carbon, which is equal to the present value of the flow of expected marginal damages at the high discount rate, whose level I've been discussing mostly in this presentation. This kind of approach lead me to use a discount rate between 1% and 2%. Okay, between 1% and 2%. And if you go back to the first slide that I presented in this presentation, you see that if you use something between 1% and 2%, well, maybe 1.5% is illustrative, you see that you need to use the social cost of carbon, which is quite large. I mean, maybe larger than $300 per ton of CO2. And that's my conclusion. Thank you, Philippe.